It's a little device here that will shoot a projectile. Little spring here. I'm going to compress the spring. And when I do that, I put a projectile here and watch this gang, little spring gun. Out it goes. No surprise. But I've got another ball that I can put on the end here like this. And when I go like this, it falls essentially straight down. A little bit out, okay? But kind of down it. This one goes outish. Now I'm going to do it both at the same time. When I do them both at the same time, you guys got to figure out, hey, which one's going to hit the ground first? The one that just dropped down or the one that goes out?
All right, so I want to see a show of hands before you guys see this in motion. So I'll narrow it down to three options, right? Now, you guys know the setup. Okay, it's going to hit that spring in the middle, pow, and then one ball goes pretty much straight down, the other goes horizontally out, and it's going to go to that parabola type motion. Okay? So there's three possibilities of which hits the ground first. Right? Possibility one, maybe the one that goes straight down hits the ground first. Possibility two, maybe the one that goes horizontally out. Well, maybe that one hits the ground first. And possibility three is, well, maybe they hit the ground at the same time. Show of hands. How many of you guys think the one that goes pretty much straight down is going to hit the ground first? How many of you guys think the one that goes out is going to hit the ground first? How do you guys think they're going to hit it at the same time? Oh, look at all those hands. All those hands. You guys already know this stuff.
You just think, oh, the one that's fired out, it's going to be in the air for a longer time. You know why? Because gravity is going to start to pull it and say, oh, I didn't know you were moving. Go ahead. And gravity not going to pull so hard.
Is that what gravity does? Does gravity see something in motion and then just like stop working? No, but you guys know that already because you guys just told me the answer. You're like, oh, yeah, they're going to hit the ground at the same time. You guys are saying they have the same vertical type motion, right? Let's skip ahead a little bit here.
This course, in your class, I'll say, I had a sharp class, honey. I had a sharp class, all right? All A's. But if you hear this, then you got to do your homework, okay? Here we go again. Here we go. This next moment may be very important for a lot of you who are everything riding in your grade. All right, here we go. Here we go. Listen.
So they did hit the table at the same time, right? You search, right? You could hear that, right? All right, let's look at let's roll another Paul Hewitt here. Where are these today?
Take a cannonball and you throw it up in here like that, okay? Here's a speed like this. Speed gets less. Now it starts to pick up.
All right, so you guys see he drew a bunch of velocity vectors, right? So there are lots of types of vectors in the class. Those are definitely velocity vectors, right? You guys see the direction of motion changing, but you also see the magnitude changing. See how the magnitude gets shorter on the way up, and it gets longer on the way down? That's because the cannonball is slowing down on the way up and then speeding up on the way down. Can that be true? Right? Now, the way we're going to approach this in this class is we're going to, he's about to do is break those into components and say, well, what's going on horizontally? What's going on vertically? Guys, if you know the horizontal motion, you know the vertical motion, can you put it all together with, say, like Pythagorean theorem and get the total speeds? And actually, that's kind of what you're looking at now. You're looking at like what the hypotenuses of what would be right triangles. Let's see what those right triangles would look like. Here we go. Components.
All along here, the sideways part stays the same. The sideways part doesn't change. Only the vertical part does. And that's kind of neat.
Right, here we go. Right. Yeah, so you guys see all those right triangles? Right? Yeah, you guys see how the horizontal component of velocity is the same all the way across? Okay? So if you were up here in a blimp watching this cannonball go across, it would look pretty much constant speed going across the field, wouldn't it? Okay? Versus vertically, do you guys see how it changes? In fact, how much is it changing vertically every second? About 10 meters per second per passing second, right? So for example, right here, say it's going strictly up at like 30 meters per second. How fast is it going up here? 20 meters per second, and then 10 meters per second. And what is the vertical component of velocity right at the peak? 0, right? So it's the cannonball isn't moving up or down. Now it's moving to the side, just not up or down. Okay, great. Oh, let's do last one of these demos today. So animation, projectile motion cannon. Right, we got the total velocity and then split into components. Look at that. Right now, this looks a little different than how I would do it or Paul Hewitt did it. Right, because here's what I would do. I would take this green vector and slide it over, connect it tip to tail with that red component. Right, make like a little triangle. You guys see a little right triangle that would be right. So the orange vector is the total speed, and then the red and green are just the components. Right, let's check this out throughout its flight. Throughout its flight. Here we go. Ooh, look at that. Right, let's go. Let's look at that a few times. Right. So I definitely see that the orange vector is kind of getting smaller on the way up and then larger on the way down. But it's kind of hard to make sense of that unless you break it into components. How about that red one? You see that red one is the same all the way across, right? The red one's not changing because there's no horizontal force. Right? Of course, we're ignoring air drag. We've been ignoring air drag. We're still doing that, right? Hey, and that green one is changing by 10 meters per second every passing second. Ah, right? And then if you put the red and green together, that's how you figure out how long that orange one is using Pythagorean theorem. Right? You guys get that? Right? All good? Right? Because if you follow just these first few minutes of class so far, that's it. That's projectiles in a nutshell. Right? You guys ready to switch over and start solving some stuff? Solve stuff time. All right, so you guys have a page. Well, brand new page. One of the pages you have looks like this. Okay, you okay, this? Okay. Now, this page, these are all projectile questions. And there's different setups you can do. So if you start reading the scenarios, everything on the left side, like these 3 scenarios on the left side, all involve a cannon perched at the top of a cliff fired horizontally. Okay? And then the scenarios on the right side involve a cannon like on the ground, angled up at some angle. Okay, so a little bit different setups. And let's do one of each of those scenarios today, and then tomorrow when you guys are with a substitute, you can help each other out and solve a bunch of these other ones, right? If you can do this independently, that's a good indication you know how to solve these, right? Even before you read the scenarios, do you guys see just in the how I gave you guys the data in these tables, right? So you guys remember it's the same 5 variables: time, acceleration, displacement, initial velocity, final velocity. But now we've got both horizontal and vertical. And even at a glance, you can tell which part, like which table goes to which data, right? Because horizontally, remember, there's no acceleration because there's no force. So horizontally isn't just horizontal displacement, horizontal component of velocity and time, right? XVT, right? Like there's no acceleration vertically, but vertically, or sorry, there's no acceleration horizontally. That's what I meant to say. Right? But vertically, well, I do have to consider acceleration. So there's also that variable. Right? We got free fall gravity. You see right there. And because it's acceleration, it's also changing velocity. So we've got initial final velocity vertically. Right? You guys see how that's laid up? Right. So that's a very forest for the trees view of like, solving projectile problems. Like, okay, what variables do you have and what can you possibly solve for? Okay. So let's do the second scenario here. We're going to do number 5 through 8 for the notes. Right? Number 5 through 8. Okay. Now, my numbers are different than your numbers, and your numbers are probably different from your teammates, but everybody has the same scenarios. Okay. So we've all got a cannon firing a cannonball horizontally at the edge of a cliff. And I told you what the cliff height is. Right? Everybody has a different cliff height, but well, right, you know what your cliff height is. Right? And then I asked you a bunch of questions. So how much time is to reach for the cannonball to reach the ground? How far does the cannonball land from the base of the cliff? Horizontal displacement. What's the vertical component of velocity, right? It's about to hit the ground, and what's the total speed that the cannonball crashes into the ground? Okay, so we all have those questions. Okay? And let's see what I gave you. Ooh, I told you how fast the cannonball is going horizontally, which when I draw the picture, if you don't see it now, you'll see why that must also represent the blast speed of the cannon. Right? So that right there, that's how fast the cannon is firing the cannonball. Okay? I told you the gravity field. So it looks like today we're using 9.8 meters per second squared. So that's okay. We can do that, right? I told you the height of the cliff. Right? And you know, maybe I should not have explicitly given you this number, but I bet you could figure it out. Because if you fire a cannon straight horizontally, then when the cannonball is leaving the cannon, how fast is it traveling up and down? 0. That's why that number is 0 for everybody. Is that? The fact that V initial in the y direction is 0 aligns with this detail that the cannonball is fired horizontally. This is the same thing. Okay, you guys get that? Okay. So I really I'm kind of overdue to draw you guys a picture. So this is number 5 through 8. So that scenario. Okay. So got ourselves going on cannon, firing a cannonball right at the edge of the cliff. Okay. So we throw on a velocity vector here. I'll call this v sub x. Right. Notice I'm putting subscripts on these v's now to indicate direction. Right. This is something we haven't done last couple of weeks. We said initial velocity and final velocity, but it was just all on one axis. Now I have to separate out what's horizontal and what's vertical. So the subscript x refers to horizontal information. We know the height of the cliff. So you can call this y or h, maybe like h for height, or y for like vertical displacement. Okay. Now, could you guys imagine the path of the cannonball is probably gonna do something like this? And right about there like that. Hey, and what shape is that again? The parabola. You guys think the vertex of the parabola is right here, right? The nozzle, because it's firing horizontally. Okay. Let's before I just start plugging and chugging, let's play around with some variables. Can you guys imagine if you turn gravity off? Boom. What would how would the motion change if there's no gravity? What would the cannonball do? Yeah, just go a straight line forever, right? Just straight lines. By the way, it's called Newton's first law of motion, law of inertia. We haven't quite got there yet, but that's what it would do, right? Now let's turn gravity back on. Okay, so now we got a parabola. We're back to that. And one of the questions, ultimate, we're eventually going to answer is, what is the horizontal displacement? And I will call that x. So this week, whenever you see x for horizontal, well, x refers to horizontal displacement, right? In contrast to vertical displacement, which might be h or y. Okay. All right. Start labeling numbers. So my blast speed is 190 meters per second. Right? You guys have a different blast speed. Right? It's also a horizontal component of velocity. I told you the height of the cliff. Now my height is this many meters. You guys have a different height. And you also know gravity field is 9.8 meters per second squared, and that's downwards. Right? Like it's as a vector, that'd be down. Right. Now, just at a glance there, do you guys like feel intuitively that there is enough information that you could solve for where the cannonball lands just with the information on that page? And also, it's crash speed. That's going to be another question we're going to get to. Okay. You guys get the part? Okay. Now, let me take this table of data and I'm going to blow this up. Okay. Add a little bit of context. Okay. Because there's two axes that we have to keep track of now. There's what's going on horizontally, and there's what's going on vertically. Vertical. Right, so horizontal and vertical. Okay. Now, horizontal, there's only 3 variables that we care about. Horizontal displacement, velocity in the horizontal direction, horizontal component of velocity, okay. And then t time should be in seconds. So I just realized I typed it a little bit different than I wrote it here, but you guys get the idea, right? Okay. So how many meters per second, and how many seconds, right? And I only care about those 3 because there's no acceleration horizontally, because there's no force horizontally. Gravity doesn't pull horizontally. Okay. Gravity pulls vertically. So on the vertical side, well, now there's more variables to juggle because of the acceleration. So there's also time. I mean, you guys know I'm just going to do tax VV, right? Okay. Except instead of, so acceleration meters per second squared, okay. Except instead of x, I'm going to call it y because vertical displacement to distinguish it from this. It could still be meters though. And then velocity initial in the y direction and velocity final in the y direction. Just to hone in exactly on what's going strictly vertically. Meters per second, meters per second. Okay. And this is just one framework for thinking about projectiles, but pretty inclusive. You guys get so far? Everybody? Okay. And then let me copy paste some numbers in here. So we know the blast speed of the cannon, and therefore horizontal component of velocity is this many meters per second. You guys know gravity is pulling down meters per second squared. Let's call it down the positive direction. Everything can just be positive numbers. So that's nice. And here's the height of the cliff that's going to fall down. Okay. And you also know the fact that you aim the cannon strictly horizontally means that the cannonball leaving the barrel is not moving up or down. So the initial vertical component of velocity, you guys told me, must be 0. It's not moving up or down, leaving the cannon barrel. Of course, that quickly changes, but initial is 0. Okay. Okay. Any questions so far? Okay. All right. Now, if I wanted to answer a question like how far, like where does the cannonball land? Okay. How far does it land from the cliff? Okay. Horizontal displacement. Can I answer that right now with this? Right. For example, if I told you you're moving so fast along the interstate, you say, how far do you go? You can't answer that unless you also know what? How much time? So, there's not enough to solve there, is there? Okay. But if you think about these 5 variables, remember how many of these you have to solve anything? Is 3? And there are 3, right? Boom, boom, boom. So vertical stuff is solvable, isn't it? Right? In fact, a good thing to start solving for might be the amount of time, wouldn't it be? Right? Now, if you want to solve for time and you have all this stuff, then which kinematic formula is going to be the fastest way to get there? First, second, or third? First. Yeah, I like the first one too, right? Because the first one, you know everything except for time. So let's try that. So I'm going to go y equals v naught in the y direction times t plus 1/2 gt squared. Okay. So it's just a modified version of that, right? Okay. Now I know initial velocity is 0. So that gets rid of that term. Okay. So now we're just cliff height is 1/2 gt squared. Wouldn't that be true? Okay. And see, we're solving for time and we should know everything else. Okay, is that okay? Now, looks like my cliff height is 21 meters. And I know it's falling down at a rate of 9.8 meters per second squared. So, so I can definitely solve for how much time it was falling for, right? And maybe I should have started with this idea, but doesn't that make sense that the height of the cliff would constrain however much time it's in the air for? Like if you had a super tall cliff, it would be in the air a long time, right? Take a look at this picture. Right? See, guys, if my cliff height was like 0 meters, wouldn't the cannonball just boom, just immediately hit the ground? Right? And then the taller the cliff, right? The more time it's in the air for, and then the further it's going to go. Okay? You guys see how this is all connected, right? All connected. Okay. Can you guys solve for time? A little bit of algebra, right? Half 9.8 is 4.9. Divide both sides by 4.9. And then take the square root. So many seconds. Got my units. Right? Let's see what that is. That looks about right. Just many seconds. Right. So that right there is the hang time of the cannonball. So from the moment it leaves the cannon barrel to the moment it crashes on the ground, well, that's how much time it takes. Okay. Right. You guys did that for the numbers on your paper. You guys got a time? Ask one of those multiple choice options. Everybody right? Okay. Okay, so now I know that. We go back up to my table of values, and I can say this time right here, okay, for it to fall that distance with this acceleration starting from rest, it takes this much time. And of course, seconds. Okay. Hey, if this cannonball took, okay, maybe I'll round it to about 2 seconds, right? If it takes 2 seconds to fall this distance, do you think it also takes 2 seconds traveling across the field? Right? From point A to point B, isn't it the same time whether you analyze it vertically or horizontally? It's the same time, isn't it? Right? And that's the only variable that you're allowed to transfer over here because that's a scalar value. You guys notice that all these other quantities are vector values, which means they're either strictly horizontal or strictly vertical, but not time. Time is a scalar. Time is the same either way, right? So if it takes 2 seconds to fall, it also takes 2 seconds to go across. If you know it takes 2 seconds to go across, you know how fast it's going across, which is a constant value, not speeding up or slowing down horizontally. Hey, can you put these two guys together and solve for that? Let's do that. Let's do it. Now we know that. And you go horizontal displacement equals horizontal component velocity times the time. So this many meters per second for this many seconds. Looking at this many meters. So that's where the cannonball lands. That many meters from the base of the cliff. Questions so far? Everybody good? Just working out for you guys too? All right, so where are we here? So we've answered number 5 and number 6. So everybody should have number 5, number 6 done. Okay. Now, questions 7 and 8 kind of go together. Question number 7 is kind of a step up to question number 8. Question number 7 says, what is the vertical component of velocity right as the cannonball is hitting the ground? Okay. So if I go back over here, okay, as this cannonball is crash landing on the ground right here, it's kind of doing, well, it's crash landing on an angle probably about something kind of like that, right? I'll call it V crash. V crash. Right there. Okay. And to solve our V crash, if I looked at the components, then that's the way I'm going to solve this. This V crash is kind of going across at some horizontal component velocity. And also it's kind of coming down at some V final in the Y direction. Is that true? Right? Hey, this Vx here, is that the same thing as that Vx right there? Is that the same Vx? It's the same Vx. Horizontal component velocity stays the same all the way across, right? Horizontal component velocity stays the same. Okay. Now, kind of getting ahead of myself, because the question we're trying to tackle strictly right now is, what is this equal to? What is V final in the Y direction? What's the vertical component? Okay. Do you guys know how to get that? Can you guys do VF in the Y direction equals V naught in the Y direction plus GT? Right? Doesn't that look a lot like the second kinematic formula? Just adjusted for strictly in the vertical direction. Okay. And I know this is 0 meters per second. This is 9.8 meters per second squared. I got this many seconds. There you go. Okay. Now, remember that's V final in the Y direction strictly. Okay. So we're still just focused on vertical information, just strictly vertical information. Okay. That's this right here. That's not the total crash speed though. That's just the vertical part. Okay, you guys get that? Okay. Oh, but I do know what this is. This is what this is. Talked about that already. Right, just copy paste that right there, and then change. Right. And if you know how fast across, and you know how fast down, can you put those together and solve for this hypotenuse of this right triangle using the Pythagorean theorem? But you can do that. Right. So the last part, V crash squared for software is equal to V sub x squared plus V final in the Y direction squared. That's just Pythagorean theorem, isn't it? Let me go spell that out. Pythagorean theorem. Pythagorean theorem. Okay. So V crash squared is equal to, this number was this many meters per second this number was this many meters per second. So square them, add them up, right? And then I'll throw in a middle step here. We get a crazy big number. So I'm one algebra step away from getting the answer. What's that final algebra step? What do you do to both sides? Square root. Yeah, square root. I think I showed you guys a fancy way to do a square root. Just power 1/2. So V crash equals, all right, so this is the total speed coming in on an angle. 191 meters per second. Let's check that. Yeah, so here's the answer to number 7. Here's the answer to number 8. That work? Yeah. All right. I'm seeing both those as answer choices, so that is good. One kind of interesting thing I want to mention here too is notice how fast across versus how fast down. 190 versus 20. You guys see I'm gonna have actually a very skinny triangle, so the hypotenuse is not a whole lot different than the longest leg of the right triangle. But do you guys remember that by doing that trig lab a few weeks back? Okay. All right. You guys good on scenario 5 through 8? Okay. So 5 through 8 is done. Okay. The other scenario we're going to do today is, let's do 11 through 14. So 11 through 14. So this one says cannonball is fired at this speed at an angle of so many degrees above the horizontal on a flat plane. Find go through this list. Horizontal component of velocity, initial vertical component of velocity. Those are really just starter steps to help you answer other questions. The total of okay, so the hang time for the cannonball, how much time to go back down to ground, and then finally, how far did the cannonball go horizontally, which really might be like the question you'd be most interested in, right? In fact, I bet if you guys go to college and take physics again and get a projectile question, they might give you this setup and then just skip straight to question 14. But of course, you'd have to answer these other questions to answer that question, right? I'm helping you guys out by asking all these leading questions, right? All right, so let's get a picture for this cannonball on a long flat plane. So it's got a cannon. Cannon. Oh, whoops. You see back out again. All right, there we go. Right. So it's on a flat plane. There's this cannonball being fired at some speed at some angle. Okay. So I'll call this V blast. Okay. And thinking ahead a step here, you guys know kind of where this is going, is that I'm going to have to analyze what's it doing horizontally and what's it doing vertically. Right. So let me go ahead and break this into components right now. Break this into components. Here's how fast it's going across the field. Here's how fast it's going strictly up, leaving the cannon barrel. Across, up. Okay. I told you guys this angle right here. Hey, if you know the blast speed and the angle, can you solve for those components? This sure does look like sine and cosine. You guys remember a few weeks back doing sine and cosine? Right? Actually, let's do this in terms of variables. What's this bottom leg down here? It's what times what? V blast times sine or cosine of that angle. Which one's adjacent? Cosine. Yeah. Right. So I'm going to say this is V sub x equals, that's what I should have said. V sub x equals that. Okay. Now, V initial in the y direction, well, that must be your V blast times sine of the angle. That'd be true. Okay, so now you can get those components. Okay. And you know what the cannonball is going to do. What shape is that dashed line right there? As a parabola, right? Then hang up somewhere over here. Okay. We're going to answer a bunch of intermediate questions so we can ultimately answer what is the range of the cannonball. That's to say, what's the horizontal displacement x? Okay, that's eventually where we're headed. But that doesn't x. Okay. All right, so one thing at a time. I need some numbers. So let's go 190 meters per second at a 25-degree angle. Your numbers were different than mine, but everything was the same up to that point, right? Okay. So v sub x is whatever 190 cosine 25 degrees is. Find out. 190 meters per second, cosine 25 degrees. I'm looking at 172, throw an extra decimal just for fun, meters per second. Okay, so I bet that's going to be an important value. Let me definitely hold on to that. Okay, that's how fast it's going across the field, isn't it? Okay. In fact, if you did know the hang time, you could just take that, multiply by the hang time, you'd have the answer, wouldn't you? Okay, but how would you get the hang time? Well, I bet that has something to do with this vertical motion. That's going to constrain the hang time, right? Okay. So let's get that. Well, I know the initial velocity in the y direction is the blast speed times the sine of that pitch angle. Okay. In the calculator, all I have to do is scroll up, scroll over, and where the cosine is, pop in a sine. And that gives me the initial in the y direction is this many meters per second. So hold on to that number. I bet that's going to be an important number. Okay. In fact, those two numbers I just circled, I think those are two of the answers. Yeah, that is, here's the answer to number 11, and here's the answer to number 12. Okay. Yeah, to go to college, you have to kind of figure out that you would have to know those to proceed forward with the problem, but I'll put you guys out here, right? Okay. Number 11, number 12. Okay. So everybody good? Now, number 13 says, how much time is the cannonball in the air for? Because, and here's why you would want to know that. Because if you know how much time it's in the air for, if you take that time and multiply by how fast it's going across, wouldn't that tell you exactly where the cannonball lands? Right? Distance equals speed times time. You guys get that? Right. Right. So how much time? Now, I can think of at least a couple of ways to solve for the total hang time. So I'm going to take you guys through two different ways so that you get a couple different perspectives. Here's one perspective. You could use this first kinematic equation, and where this displacement is, remember this is vertical, right? Guys, what is the displacement from the ground back to the ground? What's the vertical displacement from the ground to the ground? 0, right? Can you just put in a 0 for the vertical displacement from the ground to the ground and then solve for time, right? Because I bet you would have everything else. Let's try it that way. Now, this is just one way to solve for time, not the only way. I'll go y equals v naught in the y direction, t, and this would be the hang time. I'm gonna, here, before I write anything else, because if you're blasting the cannonball kind of uppish and gravity's pulling down, isn't there going to be a disagreement in sign somewhere? Right? Like maybe positive and negative. I'll go ahead and take care of that right now and just say minus 1/2 g t squared, where t is the hang time. Okay, is that right? If you blast it up and gravity's pulling down, I already took care of the sign change, right? Okay. So we'd really like to know what is the hang time. Right? And I can plug in 0 meters from the ground to the ground for vertical displacement. Oh, I know what v naught y is. That's this number right here. Meters per second. Here's gravity. Reason this today. It's like that, right? Okay. Now, if this were a scenario where the vertical displacement was anything other than 0, this would definitely be quadratic, wouldn't it? T is being squared there, it's not squared there. But because it is equal to 0, you guys see this is going to simplify and you can bypass the quadratic formula, right? Because you can divide every single term by t. T, t, t. Hang time here, right? Okay. 0 over anything is just 0. This one cancels. And this one, well, reduces the power by 1. Okay. So that simplifies to and then half 9.8 is 4.9. That looks a lot easier to solve, doesn't it? Right. And then can you add this term over and then divide by that coefficient? So 4.9t equals 80.3. So the hang time is, okay, take this, divide by this. This many seconds. There you go. That is the answer to number 13. Well, it's one way to get there. Well, you know what I meant to do before we ever even started plugging and checking was I was going to show you that I knew it was going to be about 16 seconds anyway. But let me show you how I knew that was going to be the case. Okay? Because in the framework is actually more related to this next equation, which is the other way I'm going to solve this. Okay? Guys, if you throw a ball straight up at 80 meters per second, then how fast is it going after 1 second? 70, and after another second, 60, and then 50, 40, 30. Okay. How many seconds does it take to get all the way to 0? 8, right? If it changes by 10 meters per second every second, then you go from 80 to 0 would take 8 seconds. Do you see that? That's 8 seconds to get from here to here. That's to the peak. So if it takes 8 seconds to get to the top, does it take another 8 seconds to fall back down? But it's 8 and 8, 16, right? Let me write that out formally. VF in the y direction equals V not in the y direction minus GT. I'm just using a modified version of that second kinematic formula. Okay. Now, if I go to the peak, right, guys, at the very top, how fast is it moving vertically at the very top of the path? Wouldn't that be 0 meters per second vertically? Right? It's not going up or down just for 1 moment. Okay. And this number I'm using 80.3 meters per second. Okay. Minus 9.8 meters per second squared times t. But guys, this t, wouldn't that represent half of the total hang time? To go from here to here, isn't that half of the total hang time? Right. So where this t is, like as a variable t, I'm going to put half of the total hang time. Isn't that what that would represent? I'm going to pause this here. All right. So if you solve for, are you guys okay? Why put half of the total hang time for the t? Right. So you go from here to the peak, which is what the setup is. That's why this number is 0. Right. It's half of the total hang time. Okay. So if you solve for hang time, now you guys know what the answer is already. We found it using a different method, but let's try this out. So 0 equals 80.3 minus 4.9 t hang. Actually, that looks exactly like what we did just right over here, doesn't it? Like that. Okay. Add this over, 4.9 times the hang time equals 80.3. T equals 80.3 divided by 4.9. Some number of seconds. I dropped my units at some point, but use second. It's going to be seconds, right? So you're still going to get what we did before. Right? So there you go. There's that approach. There's this approach, but they both give you the same hang time, right? So there's multiple paths through the forest, right? Yeah, you guys good? Okay. So we've got one question to go, which is, where does this ball land? What's the horizontal displacement x? You guys remember x? Right? Okay. You could also call it the range. If you ever open up a physics textbook, say, what's the range? That's what we're solving for right now. Hey, is the range x just equal to horizontal component velocity times however much time it was in the air? Would that be true? Right? If you're driving in a car 60 miles an hour for 3 hours, did you go 180 miles? Right? You guys knew that before you were walking this class. We're just doing a version of that. So I know it's going this fast across meters per second. I know it's been in the air for this many seconds because I just showed you guys 2 different ways you could get that. So put it all together. Seconds cancel. I'm getting this many meters, and that is the horizontal displacement x. Boom, and that is the answer to number 14. So using time equals there you go. So there's number 11, 12, 13, 14. Boom, right there. All right, and that pretty well takes us to the end of class. So you guys got any questions? Anything today? All right, so like I said, I will not see you guys tomorrow. But be set up with a sub. So that would be a perfect opportunity to work with each other and yeah, see if you guys can solve a bunch of these problems. There's still a bunch of other projectile stuff I want to do with guys, like a lab and do conceptual questions. So one thing at a time. That's for today.